Hi, my name is Taylor Liss, and my paper was on concurrency models for multi-threaded processes. A process is the main unit of work in a computing system, and processes are most useful to us when we have multiple threads of execution running concurrently on multiple processing cores. One of the issues that can arise in this situation, though, is when the order of execution on shared data depends on which thread got access to that data first. We call this a race condition, and concurrency models are one of the ways we can mitigate its effect. My paper examined 4 of the more common concurrency models, which include mutex locks, actors, active objects, and functional programming. Mutex locks are one of the simplest and most common forms of concurrency models still in use today. They work on the idea that every process has something called a critical section, which is the part of its code that accesses data shared with some other process. Regardless of whether a process wants to read from that shared data or write to it, it must acquire a mutex lock prior to accessing it. Once a process has a mutex lock, no other process can access that shared data until the lock is released. For mutex locks to work, all processes that access shared data must use them. However, there are dangers with this, as if all processes are waiting to acquire a lock, you could end up in a deadlock situation. Functional programming is another concurrency model that helps us avoid race conditions. Functional programming languages have immutable objects. Immutable objects are never modified. If a thread needs to make changes to one, it actually makes a change to a copy of it. In this example, you can see how the vector, map, and list data structures in the Clojure language are immutable. Although we modify the vector, map, and list objects in this example, their original value is never lost. Because we never modify data directly, it's very difficult to make race conditions occur. This inherent thread safeness of functional programming languages can be very appealing. However, learning a functional programming language can be a real big paradigm shift. I will admit that while researching for this paper, it took me quite a while to understand just exactly how functional programming languages work, so their benefit does come at a cost. Aside from avoiding mutable state, there are other ways to avoid race conditions. An actor is an object that you communicate with by sending it messages. When you send an actor a message, it arrives in the actor's mailbox. Actors process messages in the order they were received. Because actors don't directly communicate with each other, they can operate asynchronously. Additionally, actors are thread safe because they keep track of how many messages are in their mailbox. There is no way to change their internal message count unless you send them a message. The last concurrency model I examined was the active object model. The active object model is based on the actor model. There are 4 main components to the model. The first is the proxy, which is a public method provided by an active object to its clients. Next is the dispatch queue. That's a list of pending requests that have been received from clients. Third, you have a scheduler, which determines which request should be executed first. Finally, there is a callback, which allows a result to be obtained via the proxy after a request has been executed. One important aspect of active objects is that they maintain their own thread of control. This means that a method can execute in a different thread than the one that invoked it originally. By allowing multiple independent threads of execution, you can interleave the access to shared data, thereby preventing race conditions. Although my paper only covered 4 of the more common concurrency models, there's quite a few others out there. Things like data parallelism, lambda architecture, and process calculi. Often, when choosing a concurrency model, there's a number of factors we need to take into consideration. What's our unique use case? Am I trying to solve a concurrency problem, a parallelism problem, or both? What about the systems I'm targeting? Are they geographically distributed? What architecture are they using? How resilient do I need my code to be? All of these can impact what model we end up choosing. When we do choose a model, we even need to choose things like what language do I want to implement it in, and what libraries in that language do I want to use. This is why I think learning about concurrency models is so valuable for any computer science student. Even though there are a multitude of different concurrency models out there, you can always find a solution for your unique use case. I hope you've enjoyed my presentation, and thank you very much.